Today I'm going to talk to you all about how to turbocharge your chemistry with catalysts. My name is Lawrence Crosby, and I'm a PhD candidate in the Material Science and Engineering Department. Here in America, we love our cars. It's a symbol of autonomy and freedom. And collectively, we've driven more than 3 trillion miles in 2017, and the year isn't even finished yet. And I'm sure you're all familiar with traffic and gridlock that results. This is a picture of the Los Angeles skyline showing the stark difference in air pollution in the 1960s, about 30 or 40 years ago, compared to more recent times in the early 2000s. The main difference between these two pictures is that emissions control devices and laws were put in place, and catalytic converters are a key component in making these emissions control devices work effectively, as you can see here. A catalytic converter is just a device that converts some sort of toxic gas into a less lethal one. For example, carbon monoxide, nitrous oxides, and hydrocarbons are converted into CO2, nitrogen, and water. Now, CO2 is still somewhat of a problematic gas, given that it's a greenhouse gas, which contributes to global warming. So this is still somewhat of a problem, but catalysts cannot solve that. That's a separate problem of how do we deal with our use of automobiles in the first place, in electric vehicles, and those sorts of things. But today I'm going to focus on addressing catalysts and air pollution control. So catalysts clearly work, as I've tried to demonstrate with those pictures in 2 slides ago, but they are pretty expensive. And here's a plot of platinum, which is one of the most common catalytically active materials in use today. And it's around $1,300 per ounce, which is almost as much as Bitcoin for those in the know. This is a problem, and it's gained the attention of the United States Department of Energy and the NSF, which funds the research in this area, and I thank them for being here today. It has made it possible. So, to take a step back, what does a catalyst do? A general chemical reaction, you have some kind of chemical reagent that you start with, and you're trying to make some kind of product of interest. Generally, you have to overcome this red curve, which is called an activation energy barrier. What a catalyst does is lowers the activation energy barrier, and as you can see with the new red curve, and the effect of this is that it makes the chemical reaction happen orders of magnitude more quickly than would be possible otherwise. Another way to think about this is it turns a mountain into a molehill and makes it much easier for you to get to your destination. And the effect of this is that it turbocharges your reaction. And this is an example of the current land speed record holder, which is the Koenigsegg Agera RS, which recently set the new land speed record of 277.9 miles per hour in the Nevada desert. And it just so happens to be street legal, so it actually has catalytic converters, which makes it much more impressive. So how can we better understand catalysts such that we can make better catalysts for the future? Well, one way is with microscopes, and that's what I do. I use one of these microscopes that you see on the right, which is called an electron microscope, to look at very, very small materials. Here's an example of one such material that I actually look at, which shows something that is on the order of a nanometer in size. Now, just to put this into perspective, the size of this particle, for it to traverse the catalytic converter from start to finish, would be about the same distance that it would take you and I to go to the sun. So this is astronomical differences in scale. And we can actually see this using these really powerful microscopes in order to better understand and correlate the atomic structure with the material properties and how the catalyst actually performs in the real setting. And the goal is to prevent this from happening, which you all may be familiar with, a check engine light if you own an automobile, or a failed catalyst, which is shown on the right. And we are trying to prevent this from happening because this adds to economic cost. And of course, if the catalyst isn't working, then you're producing a lot more pollutants than you would be otherwise. And this is an example of a real catalytic converter that has a honeycomb structure to increase the airflow over the very small particles that I just showed you. And the goal here is to make these more reliable such that they last longer and more economical to use less of these expensive materials like platinum. And just to take a step back, the pollution problem hasn't really been solved, at least not for the developing world, where automobiles are becoming much more popular, such as India and China. The sort of picture of Los Angeles from the 1960s is an awful lot like the way this picture here. And this was taken from approximately 2 weeks ago in New Delhi, India. So this is an important problem for the world in general going forward. How are we going to manage this problem of pollution as more and more people get the means to afford automobiles and upward economic mobility? So I hope that I've convinced you all that this is an important area of research to continue to explore and investigate in order to improve the outlook for the world and for future generations. Thank you for your time.